And we're back again. This is a solution of the 2004 number 3 free response question, which is very difficult. It has a lot of different rotational ideas in it. So what we have here is this bar, and this bar is of a certain mass, and it's uniform and a certain length. And that would mean that its center of mass would be at its center, but we're going to pivot it about a point right here, which is a distance L over 3 away from one end. And the first thing we're going to do here is that they're going to ask us, what is the moment of inertia of this thing? Okay, so moment of inertia of a bar, we can look up the moments of inertia of a bar around its center and also around its end. It's a 1/12 and 1/3 ml squared respectively, but this is around some other point. So I think the best way to get at this is to use the parallel axis theorem that says the moment of inertia around some other point is the moment of inertia around the center of mass plus m times d squared, where d is the distance you had to move to get from the center of mass to the new point. This is how we got the 1/3 for going around the end of a bar in the first place. So here we are moving from L over 2 to L over 3, which is a difference of L over 6. So what we're going to do here is we're going to say that the moment of inertia for this thing is 1/12 m L squared plus m times L over 6 squared. Okay, the ml squared terms are going to factor out, and we're going to have 1/12 plus 1/36 times ml squared. 36 because 6 squared. It turns out that 12 and 36 have a common factor of 36, well, or common factor of 12, but we're going to go to 36 as the common denominator. So we have 336 plus 136 ml squared, and that turns into 436, which is the same as 1/9 ml squared. This is the moment of inertia for this object that we're going to be playing around with here today. Okay, great, fine, dandy, wonderful. Second thing they ask us to do is, hey, this object now is allowed to swing around this pivot point from this orientation to this orientation. So it swings down, and as a result, it will be moving. It will be swinging. It will be going. And they would like to know, what is the velocity of the end of the bar or rod? Making that look worse than it was before. Okay, so this is going to be a little interesting. So at first that gives me pause and it makes me think, hey, how am I supposed to figure this out? There are a number of different ways to do it. We could figure out the torque in this orientation, right? The torque in some random orientation between these two, and the torque here, of course, is 0 because the weight is pulling straight down and there's not proper alignment for torque. And then we could integrate that torque, but really, honestly, energy. Anytime something goes and changes its position and as a result is moving, my brain screams at me energy. So we have potential energy in this first diagram, and we're going to have kinetic energy in this second diagram. And then here's where things get a little weird. I know that the velocity of the end of this rod is going to be different than the velocity anywhere else. In fact, the velocity around the pivot point is going to be 0, and the top is going to be actually going the other way. So putting the kinetic energy in terms of the linear velocity is probably a bad idea. This thing is rotating. So I'm going to write m times g times h for the potential energy, but I'm going to write 1/2 I omega squared for the kinetic energy, which is rotational kinetic energy. That is true. Every point on this bar is going to have the same omega, the same angular speed. We can use that angular speed to find the velocity of the end later. Okay, H, how far down does this thing fall? Well, it used to be up here, and now it's down here. That's the same L over 6 that we translated the point previously. Now, 1/2 of 1/9 ml squared, I mean, we found I over here, we might as well use it, times omega squared. Okay, let's be very careful about cancellations here. So we have an L on, well, let's start with the m's. We have an m on this side and m on that side, so we're not going to write m, they're going to cancel. We have an L on this side and an L squared on that side, so we're going to wind up with an L on that side. So we have G over 6 on this side left over. 2 times 9 is 18. 1 over 18. M disappeared. L went from squared to not squared, and then times omega squared. Looks like 18 comes to the top, and G over L, and that's equal to omega squared. So 18 over 6 is 3. So it looks like omega is the square root of 3G over L. Hey, that's kind of cool. That kind of reminds me of the pendulum formula, G over L, but this one has an extra 3 in there because of the pivot point being in a weird place. But we're not quite done yet. We need the velocity of the end. And the velocity of the end is omega times r. How far from the pivot point the end is? Well, that is 2/3 L. The pivot point is up here. The end of the rod is down here. So we're going to have to go ahead and multiply square root 3G over L times outside of the square root 2/3 L. Okay, just to make this pretty, I'm going to bring in all this stuff. The 2 comes in as a 4. 4 times 3 is 12. The 3 comes in as a 9. L comes in as L squared, and that cancels this L and leaves 1 L on the top, so we got GL. And 12 over 9, if we divide by 3, is 4/3, so this is going to turn out to be 4/3 GL. Excellent. That is an excellent answer to that part of the question. There are other ways to do it, and I think I talked about some of those, but this is by far the easiest and most straightforward. You don't have to think about weird esoteric things like integrating a torque function or finding the velocity of the center of mass and then trying to translate that to down here. Those things would work, but are difficult. Okay, so now they say that you're going to go ahead and you're going to take this this object and you're going to tweak it to the side a little bit, just a little, and it's going to swivel back and forth. So what they want to know off of this section is what is the differential equation that governs this motion. Okay, so for that we're going to have to analyze the torque, the restoring torque. There's a force, mg. It is located a distance of L over 6 away from the pivot point, so that's the distance away, and we have to include a term because it's not properly aligned. So I'd say that the torque, restoring torque here, is mg L over 6 times the sine of the angle. And that's going to let us write down the differential equation because we're going to start with the torque version of Newton's second law. Okay, this is mgl over 6 sine theta equals 1/9 ml squared, and we're going to write this alpha as the second derivative of theta. Okay, now we need to groom this a little bit. First of all, we have some algebraic cancellation needs to go on, absolutely. Also, we're going to do the small angle approximation and replace sine theta with just theta. So let's do all those things. Let's talk through this. M cancels M over here. This L cancels the square. G stays there. That L comes over to this side. 9 over 6 is 3 over 2 G over L. And sine theta becomes theta. And that equals d squared theta dt squared. Let me just make sure that I got that correct. I believe that's right. Let me double checking here. It's slightly different than what I got before. Yeah, that's correct. There's probably a minus sign issue to deal with here. Remember that this is a restoring torque, so this should have a minus sign on it. This should have a minus sign on it. I don't know if the College Board would tag you for that. I guess they probably would, so let's go ahead and do that. And then they ask you as the final thing, they ask you calculate the period of oscillation as it swings. Okay, that's great. We can do that post haste, like right away kind of thing. I'm going to use the red pen for this. D wants the period. And we know that when we find the omega, and not the omega for this thing, this is a totally different situation. The oscillations start here. Omega is whatever is in front of here. Well, actually, omega squared is 3/2 g over L. And that means that omega is the square root of that. So we can find the period by taking 2 pi and dividing by omega. So that's going to be 2 pi times the square root of 2L over 3G. And I don't know that we can do much more with that. I suppose we could bring the 2 pi inside the square root, but let's just leave it as it is and put a box around it. Ooh, I should have circled something down here too. 2 pi square root 2L over 3G. All right, that is the solution for this problem, and it involves quite a number of things that have to do with rotation and a lot of stuff that may or may not have taken hold in your brain very well as we learned it the first time. This problem is the second hardest problem of this type that ever showed up on the AP test. There is another problem which has a reputation of being the physical pendulum from hell. By the way, that's what this is, a physical pendulum, when it's something that's oddly shaped. And we are making some simplifying assumptions, but really we have to deal with the torques and we have to deal with moments of inertia in order to solve it. If you remembered the results for the physical pendulum, you could have just gotten this right away, because the physical pendulum results, and let me just put that down here, was that omega is the square root of mgx over I. X is the distance between the center of mass and the pivot point, and I is whatever you got. So you could have put those numbers in here and gotten this even without doing this. But we learned how to do this, and this is part of the point structure, and they walked you through it. So I was able just to grab this right here. It's all the same math. It all works out the same. Okay, thank you for your attention.